I think it's time to start. Let's get started, okay? Uh, good morning. No, good morning. Okay. Good morning, good afternoon, good evening, everyone. Welcome to this seminar on nonlinear water waves. Thank you very much for joining us. And firstly, I'd like to introduce myself. I'm Sunao Murashige from Ibaraki University in Japan. I'm one of the organizers of this seminar. I hope everyone is doing very well and all safe during these difficult times. You know, vaccinations have started, so I hope things will get back to normal soon. But still it seems that we have a serious depression around the world. Then we've decided to start this online seminar to continue our scientific exchange. Okay, this is the first time, so I'd like to explain about this seminar briefly. Let me share my screen with you. Okay. The aim of this seminar is to provide a chance to discuss recent developments on water waves, all aspects of water waves, namely experiments, computations, and analysis, everything. So we welcome anyone who is interested in nonlinear behaviors of water waves. This is the website of this seminar, and meeting format is summarized around here. And this shows the time in Tokyo, in Japan. And we plan to hold this seminar approximately once a month. And I hope this meeting format is reasonable for all of you. And if you have any advice or comment, please share it with us, the organizers of this seminar. And the list of organizers is here. And if you are interested in giving a lecture in this seminar, please let us know. And also please suggest speakers which you'd like to hear in this seminar. Okay, let's begin. Let's begin today's seminar. Today we have two speakers, including me. So I'm asking Dr. Kataoka of Kobe University for chairing today's seminar. Dr. Kataoka, please.
Okay, thank you. Thank you for your introduction. Okay, today we have two talks, and if you have any questions, we have a separate Q&A session for each talk, after each talk. So please ask questions during this Q&A session, okay? About 5 minutes, okay? So for the moment, please mute yourself during a talk, okay? Okay, so okay, let's get started. So I'm pleased to introduce the first speaker is Professor Murashige from Ibaraki University. And can you share your screen?
Yes, wait a minute. Where is my...
Ibaraki, it's a place or it is the name of someone?
Yeah, name of prefecture.
Prefecture, oh, I see.
Yeah.
Mm-hmm.
Wait a minute. Where is it?
Okay, and he's talking about effects of a linear shear current on surface waves in deep water. Okay.
Okay, can you see it?
Yes, sorry.
Okay. Okay, thank you very much for introduction. Today I'd like to talk about effects of a shear current on surface waves. This is a joint work with Professor Choi of New Jersey Institute of Technology. This figure shows the vertical cross-section taken along the propagating direction of surface waves. This blue line is the water surface. When wind is blowing on the water surface, a current can be generated and its horizontal velocity may change with depth like this. So this is the shear current, vertically sheared current. And it's well known that the interaction of surface waves with the shear current plays an important role in the ocean. And for example, it was shown that the presence of a shear current may change the breaking limit of waves, but its mechanism has not been made clear yet. The aim of this work is to numerically study the effects of a shear current on these two, which are intimately related to the onset of wave breaking. One is instability of steady gravity waves, and another one is generation of parasitic capillary waves. Here, parasitic capillary waves mean ripples, namely short waves generated on the forward face of progressing gravity waves like this. These two are strongly nonlinear phenomena, so it's difficult to numerically catch these two using the existing methods developed in the previous works. Then in this work, we introduced the conformal mapping technique. And this is the outline of my talk. Let me begin by a formulation of the problem using conformal mapping of the flow domain. Now we consider this problem on these assumptions, namely the fluid motion is two-dimensional and periodic in this vertical cross-section, and fluid is incompressible and inviscid. And also on the vertical variation of horizontal velocity of this shear current is linear, like this. And the slope of this linear change is represented by this omega, capital omega. This capital omega is called the shear strength. And waves are moving from right to left. And then it's convenient to formulate this problem in the frame of reference moving with waves, like this XY coordinate. And in this coordinate, the total velocity vector of this two-dimensional flow can be split into these two terms. The first term corresponds to the linear shear current, and the second term is the perturbed wave motion. And the vorticity of this two-dimensional flow is equal to minus capital omega. Capital omega is the shear strength, namely in the slope of this linear change of horizontal velocity of this linear shear current. And so the vorticity is constant. Then on these assumptions for this two-dimensional flow, we can show that the fluid motion of this second term is rotational. Then we can introduce the complex velocity potential F for this rotational part. And we can formulate this problem within the framework of potential theory. Okay, next, we introduce conformal mapping of the flow domain. For numerical computation of large amplitude waves, it's convenient to conformally map the flow domain in the physical plane into the lower half of a complex plane like this. We call this complex plane the theta plane or xi eta plane. And here, the water surface is mapped onto the real axis, namely eta equals 0. This is a merit to use this complex plane, and we can apply some theories, useful theories of complex functions. And also, I have to emphasize that even if the water surface changes with time, we can apply this transformation. Namely, the time-varying water surface can be always mapped onto this real axis, eta equals 0 in this complex plane. Then the mapping function between these two planes changes with time. And so this transformation is called unsteady conformal mapping or unsteady hodograph transformation. And recently, this transformation has been used for numerical computation of unsteady motion of large amplitude waves. In this work, we formulate this problem in this complex plane, theta plane. In this plane, the free surface conditions are given by these two equations, the kinematic condition and the dynamic conditions. And in this plane, the theta plane, and the water surface is mapped onto the real axis, namely eta equals 0. Eta is the vertical axis of this complex plane. And here, each variable is non-dimensionalized like this using the wavelengths lambda and wave speed c. And here, the capital omega, namely the shear strength, is included here and here. And so these two terms represent the effects of linear shear current on the free surface conditions. And here we can see there are 4 dependent variables in these two equations, namely x, y, phi, and psi. Phi is velocity vector, and psi is the stream function. So these 4 are the dependent variables in this plane, theta plane. And these are functions of xi, eta, and time t. Xi is the real part, and eta is the imaginary part of theta. And also x and y, and phi and psi, these are the real and imaginary part of analytic functions z and f. Z is complex coordinate, and f is complex velocity potential. And from analyticity of these variables z and f, x is related to y, and phi is related to psi. And particularly on the water surface, x is related to y, and psi is related to phi, using Hilbert transform H defined by this, like this. So x is related to y, psi is related to phi. So we can choose these two, y and phi, as the dependent variables in this plane. And using the formulation in this complex plane, we can numerically obtain solutions for a wide range of parameters, including large amplitude waves. First, let me show you the results of steady waves on the linear shear current. Here, steady waves mean waves progressing in permanent form with constant speed. For steady waves, the free surface conditions become like this, the kinematic condition and the dynamic condition. And here, the subscript 0 denotes the steady wave solutions. And we can numerically obtain steady wave solutions satisfying these two equations. The method of computation can be summarized like this. And this method is the same as the previous works. So here, let me show you only the computed results. These 4 figures show the computed results of wave profiles of steady gravity waves on the linear shear current for different values of omega. Omega is shear strength. And here, wave motion is periodic. So the wave shape for one period, for one wavelength, is plotted in each figure. And omega equals 0. This case is the case of no shear current, without shear current. And in this case, it's known that the wave shape near the crest becomes sharper and sharper with increase of wave amplitude like this. And the limiting wave has a corner at the crest, and its corner has its inner angle of this corner is 120 degrees. These are the results for the case of omega equals 0, namely without shear current. And also for the other cases of omega not equal to 0, we can see a similar change of wave shape like this. And what is important here is the maximum wave amplitude changes with the value of omega like this, and can be much smaller than that of the case of omega equals 0, namely without shear current. So these numerical results suggest that the presence of a linear shear current changes the maximum wave amplitude like this, and also may change in the breaking limit of waves. And also we can compute the wave speed of each wave like this. This figure shows a variation of the wave speed c with the wave steepness ka for each value of omega. Omega is shear current, and k is wave number, and a is wave amplitude. So ka is the wave steepness. And here we can see the wave speed increases with the wave steepness for each value of omega like this. And also we can compute the wave energy like this. This figure shows variation of the total wave energy, namely the sum of the kinetic energy Ek and the potential energy Ep, with the wave steepness Ka for each value of omega, like this. And here we can see there is a peak of the total wave energy around here. Namely, the total wave energy attains the maximum around here. And for each value of omega, this property can be found, namely around here, here, and here. This property is related to the linear stability of steady waves. So let me move on to the linear stability analysis of steady waves. The linear stability of steady waves has been numerically studied by many researchers, particularly for the case of omega equals 0, namely without shear current. Dr. Tanaka numerically found the characteristic instability, a superharmonic instability. Here, superharmonic instability means the instability due to the disturbance having the same horizontal scale as the fundamental waves, namely steady waves or less. And this instability occurs at this red cross in this figure of wave speed. And here we can see this critical point. This red cross is very close to the right end of this curve for the case of omega equals 0. This right end corresponds to the limiting wave. So the wave amplitude at this critical point is very close to the maximum wave amplitude. And also it's known that this instability is directly related to the onset of wave breaking. And these are the result for the case of omega equals 0, namely without shear current. Then in this work, we tried to examine this type of instability for the case of omega not equal 0, namely with a linear shear current. The method of linear stability analysis is the same as usual, namely we examine time evolution of small disturbances, y1 and phi1 added to steady wave solutions, y0 and phi0. And on the water surface, these disturbances are functions of xi and t in the theta plane and conformally mapped complex plane. And for stability analysis, we look for this form of solutions. Here, a sigma is a coefficient of time t. And so this sigma denotes the exponential growth rate of these disturbances. And this sigma is a complex number in general. So its real part determines the stability. And also we assumed these disturbances superharmonic. Then from its periodicity, these disturbances can be expanded in this form of Fourier series. Then substituting these into the free surface conditions, namely these two equations, and linearizing them around the steady wave solutions, y0 and phi0. And finally, we can get these two equations for small bj and small cj. Small bj and small cj are the Fourier coefficients of these small disturbances. And each coefficient, capital B and capital A, these are given by steady wave solutions. And furthermore, truncating each infinite series like this, we can rewrite these two equations into this form, this matrix form. This matrix form is a generalized eigenvalue problem for the eigenvalue sigma and the corresponding eigenvector BC. And each element of these matrices A and B, each element is given by steady wave solutions. And then we numerically solved this eigenvalue problem and determined this eigenvalue sigma. Let me show you some computed results of the eigenvalue sigma. This figure shows the computed eigenvalue sigma for the case of omega equals 0, namely without shear current. Here, this axis of abscissa denotes a parameter gamma defined by this using the fluid velocity q as crest and trough. And this parameter gamma is often used for numerical computation of finite amplitude waves. And this gamma ranges from 0 to 1 and monotonically increases with wave amplitude. So gamma equals 0 corresponds to infinitesimal waves and gamma equals 1 is the limiting waves. So in this figure, the wave amplitude increases from left to right. And the upper figure shows the computed results of the real part of the eigenvalue, sigma r, which corresponds to the exponential growth rate of disturbances. And the lower figure shows the imaginary part of eigenvalue sigma I. And in the upper figure, we can see the exponential growth rate changes from 0 to a positive value around here. namely from stable to unstable. So on the critical point of this instability is here. This is a critical point. And this critical point corresponds to this red cross in this figure of wave speed. And this is the result for the case of omega equal 0, namely without shear current. And then we computed the other cases for omega not equal 0 with a linear shear current. For example, we obtained this right figure, and this right figure shows the result for the case of omega equal minus 1.5. And here we can see similar type of instability around here, and the critical point is here. And this critical point corresponds to this red cross in this figure of wave speed c. Here again we can see this critical point is very close to the right end of this curve for the case of omega equal minus 1.5. So the wave amplitude at this critical point is very close to the maximum wave amplitude. And this is the result for the case of omega equal minus 1.5. And also we obtain the same result for the other cases like this. Here, each red cross point shows the critical point for each case. And if this type of instability is related to the onset of breaking, these numerical results suggest that the presence of a linear shear current may change the breaking limit like this. And also there are some other characteristic properties of this type of instability. And one of them is the relation between the wave energy and this instability. And this figure shows a variation of the total wave energy with the wave steepness Ka for each value of omega. And as I said, there is a peak of the total wave energy around here, here for each value of omega. And particularly for the case of omega equals 0, namely without shear current, Dr. Tanaka numerically found this peak of the total wave energy is related to this type of instability like this. Here, these two figures compare the computed results of variation of the real part of eigenvalue sigma r, namely the exponential growth rate of the disturbances and the total wave energy near the critical point of this instability. Here, this axis of abscissa denotes the parameter gamma. So wave amplitude increases from left to right. So here we can see the total wave energy attains the maximum here. And this point agrees with this critical point of this instability. This agreement is one of the characteristic properties of this type of instability. And this is the result for the case of omega equals 0, namely without shear current. Then we examined this property for the other cases of omega not equal 0, namely with a linear shear current. Then we obtain the same result. For example, this is a result for the case of omega equal 0.6. Here we can see the peak of the total energy agrees with the critical point of this instability. And also this is the result for the case omega equal minus 0.6. Again, we can see the same property. And also this is the result for the case omega equal minus 1.5. Again, we can see the same result. Now we obtain the same result for all values of omega. So from these results, these numerical studies, we found some essential properties of this superharmonic instability do not change with the value of omega. However, the critical point changes like this. These are the main results of our numerical works. And also, it should be noted that we have another theoretical approach using the Hamiltonian formulation. And Dr. Warren derived the canonical Hamiltonian system for water waves on a linear shear current. And also Dr. Sato and Dr. Yamada, they analytically investigated this type of instability and proved this relation between this type of instability and wave energy. And I think their theoretical works and our numerical works complement each other. Okay, next let me turn to another effects of a linear shear current, namely the effects on plastic capillary waves. When relatively large amplitude waves like this is progressing, sometimes you can observe short waves are generated on the forward face of progressing gravity waves like this. And these short waves are due to surface tension. So they are called parasitic capillary waves. And first, let me show you some experimental results of these waves, parasitic capillary waves. These experiments were performed by Dr. Duncan and his group. And these two figures show the side view and the top view of the water tank. And they generated periodic waves using this wave maker and try to catch the time evolution of wave shape using this camera moving with waves. This photograph shows the side view of the waves at the initial stage near the wave maker. And in this photograph, this line is the water surface. I hope you can see it. This line is water surface. And the waves are moving from right to left. So the left side is the forward face of these gravity waves. This is at t equals 0, time t equals 0. And with increase of time t, this wave shape changes like this. This is at t equals 0.028. This is at t equals 0.057. And around here, you can see a short waves are generated on the forward face of gravity waves. These are parasitic capillary waves. And with further increase of time t, this wave shape changes like this, and finally breaks and turns to the turbulent stage. Let me show you again from the beginning. And this is at t equals 0, and wave shape changes with time t like this. And putting these together, we can observe the continuous change of wave shape like this. Here, A, B, C, D, E, F. In this order, time is increasing. And around here, we can see a parasitic capillary waves are generated. And around here, a wave start to break. And this is one of typical patterns of wave breaking. And in this experiment, there is no shear current. Then in this work, we try to examine, numerically examine the effects of linear shear current on generation of parasitic capillary waves. And for that, we have to include, oops, I don't know why. Doesn't, oh, it's okay. We have to include the surface tension term in the dynamic condition on the water surface like this. Here, WE denotes the Weber number defined by this. And here, this capital T denotes the surface tension. And using these two equations, we can update Y and phi with respect to time T. And the method of computation can be summarized like this. First, following the spectral method, we expanded these two dependent variables, Y and phi, like this, in the form of Fourier series. Here, each Fourier coefficient is a function of time, t. And for time integration, we used the Runge-Kutta method of fourth order. And as initial values, we adopted steady gravity wave solutions on linear shear current, like this. And these are the same as before. So these are steady gravity wave solutions of on linear shear current, and particularly pure gravity waves. So in the presence of the surface tension term here, the solutions change with time, particularly the wave shape changes with time. So as a result, parasitic capillary waves may be generated. This is one of the methods to numerically generate parasitic capillary waves. Let me show you some computed results. First, I'd like to show you the case of omega equals 0, namely without shear current. And these two figures show initial wave solutions at t equals 0. The left figure shows wave profiles of 4 different initial wave solutions. Here, a wave amplitude is different. And each wave is moving from right to left. and this XY coordinate also is moving with these waves. And the right figure shows the corresponding the slope of the water surface, theta, which is defined by this. So this theta denotes the slope of the water surface at each point on the water surface. So in this right figure, this axis of abscissa denotes the x coordinate, x, which is the same as the left figure. And the coefficient of surface tension term is fixed to this value. And these are initial wave solutions at t equals 0. And with increase of time t, these wave shapes change like this. This is at t equal 0.5 pi. This is t equal pi. This is t equal 1.55. And here we can see short waves are generated on the forward face of gravity waves. Now waves are moving from right to left. So the left side is the forward face. And these short waves are plastic capillary waves. And with further increase of time t, these wave shapes change like this. So from these results, we can see plastic capillary waves can be generated for the case of large amplitude waves, but not for small amplitude waves. And these are the results for the case of omega equals 0. Next, let me show you the case of omega not equal 0, namely with a linear shear current. And these two figures show the initial wave solutions at t equals 0. And the left figure shows wave profiles of 4 different initial wave solutions. Here, the value of omega is different. And the red line is omega equal minus 0.1, and blue line is omega equal minus 0.2. The green line is minus 0.3, and magenta line is minus 0.4. And with this change of omega, the wave amplitude decreases like this. And the right figure shows the corresponding slope of the water surface, theta. And these are initial wave solutions at t equals 0. And with increase of time t, these wave shapes change like this. Again, doesn't work. I don't know why. Oh, it's working. This is initial waves at t equals 0. With increase of time t, the wave shape changes like this. And here we can see, again, we can see the short waves are generated on the forward face like this. These are plastic capillary waves. And with further increase of time t, we can get these computed results. So from these, we can see, even if the wave amplitude is very small, the plastic capillary waves can be generated in the presence of shear current, linear shear current. This may be related to the curvature of the water surface. And I examined the curvature kappa of the water surface like this. Here, the curvature kappa is given by this. And the right figure shows the curvature of the water surface of initial wave solutions like this. And here we can see, even if the wave amplitude is very small, like this magenta line, and the curvature, corresponding curvature can be relatively large near the wave crest, like this. X equals 0 corresponds to the wave crest. And this may be related to generation of these plastic capillary waves. And also, as shown in the experiments, the generation of capillary waves, plastic capillary waves, is related to the onset of wave breaking. So these numerical results suggest that the presence of a linear shear current may affect the onset of wave breaking. This is the same result as the linear stability analysis of steady waves. Okay, finally, I'd like to summarize my talk. In this work, we've considered the effects of a linear shear current on these two, which are related to the onset of breaking. We numerically investigated these two using unsteady conformal mapping. From these numerical studies, we found that the presence of a linear shear current may significantly affect the breaking limit of waves. We plan to continue this work for further understanding of wave breaking. And that's it. Thank you very much for your attention.
Okay, thank you Thank you very much for a nice talk. Are there any questions or comments? Professor Chapchow? I don't know how to. Yeah, please.
No, I was clapping. So
oh, sorry. Okay.
Yeah, it was not a raise.
Okay.
Yeah.
Okay. Are there any questions?
But I think Nail has one.
Yes, I wonder why you call them parasitic capillary waves, because they naturally appear, so why they should be parasitic?
The reason why we call them parasitic capillary waves, these were named by Longet Higgins, so I don't know exact origin of this name.
So perhaps somehow they break the basic wave, fundamental wave. That's maybe the reason for being parasitic. Like viruses kill people, so they are parasitic. And so these capillary waves perhaps also kill the basic wave.
You mean the parasitic capillary waves killing the basic wave? The basic wave means this basic gravity waves, right?
Yeah.
What do you mean by killing?
Well, maybe it will break and then disappear.
Disappears means, yeah, actually, these experimental results show that it's really related to the onset of wave breaking, but I don't know mechanism exactly yet. But
perhaps just higher frequencies appear, and that's their role, maybe.
Yeah, I think so. Thank you.
Okay, please, Professor Chapchow.
Thank you. Yeah, so I actually have a question regarding these experiments, Duncan experiments. So can you maybe describe the initial condition applied to the wave maker? So how could they, so have they generated already waves close to the onset of breaking from the start? Or have they?
I think the initial wave is a moderate amplitude. This is a initial condition.
I see.
The periodic waves, this is a value of wave steepness. A is wave amplitude.
Yes, I see.
And this is frequency.
Okay. But it's not close to 0.44, right? So
not close to 0.44, not limiting wave. It's
okay.
Moderate amplitude. Yeah, I think so.
Okay. And do you think would be a difference if they would have had like another type of wave maker? Like, because they use a plunging wave maker there, right?
Yeah. Actually, I don't know. I'm not so familiar with the experimental stuff, so I'm sorry, I cannot answer.
No worries. Okay. Thank you.
Yes, on this picture, which is on the screen, why there are two fronts?
Two what? I'm sorry?
No, not this one, the other one. Yes, this picture, there is a maximum of the wave. Then there is a tail. And there are two fronts. Why there are two fronts?
These two lines, right?
Yes.
Yeah, actually, this photograph is not just side view. It's a little bit, this camera is taking this photograph from the little bit front side, not just the side. So this is, I think this is a forward face.
So yeah,
so
this is
this is the crest line. Yeah, yes.
And what is this second one?
Second one, you mean this one?
No, the other one.
This one?
Yes, this one.
This is a water surface. And I think this is maybe crest line, I think.
That's what?
Crest line. It's this is two-dimensional waves, so it's hard to explain. So, this is the water surface. I mean, the water surface of the side view. Okay.
It's not one-way propagation.
This is the one wave. Just one wave. I mean, the periodic wave. One wave. One wave. One wave means it's a. This is the setup of experiments and completely two-dimensional setup. So the crest line is parallel, like this. And but the camera is not just side, not just a side view. It's a little bit front side. So, so oblique.
Is it a picture is made from the glass?
Yeah, I think so. Yeah, yes, yes, glass. So,
side.
yeah, yes, I think so.
Yes. Yeah, very strange. I mean, maybe you know why there are two fronts.
Just two fronts.
No, it's just this is as actually Sunao was mentioning. This is so the line on the left here is a crest line. So it's the one which is transverse to the propagation of waves, and this is the one you see which actually is you see at the wall. So the other line there is a crest line, right? It's the one which is transverse. It's just the angle of the camera which is from pointing downwards, looking up, and then you see this three-dimensional wave in a sense, but it's just unidirectional propagation.
So it's optical illusion. Is it optical illusion?
No, it's just the angle of the camera. So you can see the crest line at the same time the side more or less on the glass.
Okay, what on the back of the back tail of the wave, there is also some kind of structure. And what is that?
Structure, what images?
Yes.
Oh, yes, the structure. What is that?
I'm sorry, I don't know. What this changes? I don't know. What is? I'm sorry, I cannot answer now. Let me check again.
So it's someone else's experiment.
Yeah, that's right. Dr. Duncan's.
May I ask a question, please?
Any questions or comments?
Yes, may I ask a question?
Yes, yes, please.
Yes, hi, Sunao. This is, well, to everybody also, hello, this is André calling from Brazil, quite far away. So for me, good morning did work. Maybe the only one, or Wu Young also. Me and Wu Young, good morning works. I don't know exactly where Wu Young is right now. Maybe, yeah, Rio de Janeiro, that's right.
Wow.
So Sunao, thank you very much. And actually for sending the announcement and so on. So one question, I mean, how far, maybe I missed it, I don't know, how far can you go with your unsteady conformal mapping into the wave breaking profile, right? So how far can you go with this without having numerical problems or so on? Also, the instability not kicking in. You have the unsteady conformal mapping, which means you can evolve this in time, right?
Yes, I can apply this method to unsteady.
Can you get like with the onset of wave breaking, you can get basically the steepening of the front and so on and so.
Yes. This time I talked only about the linear stability analysis.
The linear stability analysis, okay.
Yeah, okay. But in principle I can do that. Actually, in the latter half we applied this method to unsteady computation of plastic capillary waves. Actually, this is related to what you talk about. Wait a minute. This is unsteady computation, and the wave shape. The largest wave becomes, it's changing to, it's not yet overturned, but it's close. I could.
It is steepening, right? So So let me maybe help you in terms of what I'm thinking. So from what I presume, and also those papers from Fructus and Karif and so on, these things take place very quickly. I think computations is probably when these things break down very quickly and so on. And now a question that I'm not sure I know I don't even have a hint is like, I have been at one point interested with waves with vorticity in looking at the submarine dynamics, meaning particle dynamics generated by the wave passing, and there's like stagnation points, Kelvin cat-eye, critical layer formations, and so on. And I was wondering if anybody, with an unsteady code, like maybe you guys have, whatever, or anybody else has looked at the submarine dynamics, meaning what happens when these guys start steepening. For example, will a critical layer vanish? Will a stagnation point not be a stagnation point anymore? I'm sure these are not easy questions and maybe unanswered or even untouched. So that's why I wanted just to double check.
Thank you very much. Very nice, interesting questions. And actually, I've never tried to consider, you said submarine, right?
Yeah, submarine just is the name I give for like looking beneath the wave.
Beneath the wave, yeah.
Yeah, the particle dynamics, because as a wave passes by, right? So there's a lot of work by analysts and numerical work of the particle structure beneath a nonlinear wave. Okay, and if you have vorticity tuned right, you can get something the analysts proved and could not find, and numerical computations were done not only by me and a student, but other people had done this too, is finding stagnation points, which are points that move with the wave speed. Usually points would move slower than the wave speed. And there's like the Stokes drift and all these things. And then there's this structure, which is a beautiful structure, which is the Kelvin cat-eye structure, which is recirculation zones that can be formed only when the vorticity is non-zero and tuned with the right parameters. So the question that I don't know the answer, and I'm interested in knowing anything, I mean, even is that when on the onset of wave breaking, how does that say at least starts deforming the Kelvin cat-eye formation, so on. But since these things are difficult, you see, with a former two students, we looked at this. It's a JFM paper. We looked at this for linear waves, because with nonlinear waves, there's these instabilities. So we look at the Kelvin cat-eye interaction with topography for linear waves. So I'm very curious to learn about what happens with nonlinear waves, the onset of breaking, and so on. But anyway, I don't want to take too much time, and also Amin's going to be speaking next. So just throwing out questions that probably, well, I don't know the answers, and probably there are no answers at this point.
Actually, I focused on the surface wave motion. I've never considered
just
thank you
maybe
very nice indications. I'd like to think about it more carefully. Thank you very much.
Well, thank you.
Okay. I think now it's time to move on. Okay. Thank you. Thank you for your nice talk, Professor Murashige. Thank you.
Thank you very much.